Hey, good afternoon, everyone. Thanks for coming for this session. I know there's a competing session, and I appreciate the one enthusiastic person who said yay really loudly, by the way. Person in red shirt who's looking down now. Look, I suspect everyone at this conference has heard the term deep learning about 83 times by now, but you're going to hear it about maybe 20 more times in this one presentation today. IBM is best known when one thinks about AI, everyone thinks immediately Watson when you think about IBM. I'm not in the Watson group. The way you should think about AI at IBM is there's many business units, many product lines, many development teams, research teams working on different aspects of AI. Watson is one manifestation, and Watson is targeted at application developers who don't know much about machine learning and deep learning. So for example, they have a voice API that you can just put into your mobile app. I focus more on data science, data scientist, machine learning, deep learning, and today I'm going to talk mostly about deep learning. Let's see if I can make the clicker work. Depends on which direction, I guess. There you go. So, there's been a lot of interest and noise around both deep learning and AI, and the press is every day there's an article about AI. But really, these two charts in my mind encapsulate why the interest has happened. Right? Fundamentally, deep learning is a method or a sub-method in machine learning, and the reason why it's exciting is that the more data you give deep learning, usually the more accuracy you get out of the model. Thank you. And that's really what the left-hand side chart is saying. And people have used the word insanely accurate, right? Unreasonably accurate. That's my favorite. Deep learning is sometimes unreasonably accurate. And in fact, if you look at the hype, the right-hand side chart is the hype chart, which is the number of Google searches on deep learning. So that's a Google search trend chart. And I got started working on deep learning in 2012, so I was before the hype cycle. So I've ridden this cycle. And I was at NVIDIA before I came to IBM, so I've seen this hype cycle pretty well. But you can see that there is an enormous amount of interest around deep learning, a large number of people who are using it. And it all comes down to the left-hand side chart, though. It's the accuracy that it gives you on a certain class of certain types of data and certain use cases. So just to give you an idea, in particular, computer vision has been revolutionized by deep learning. So before deep learning happened, most traditional machine learning methods, computer vision methods, we were getting about 26% errors. In other words, our models were 74% accurate in detecting objects in an image. Humans have a 5% error rate. What that means is if there is let's assume this is a Starbucks coffee cup and this is obstructing most of it for me, I can still guess that that's Starbucks based on the peripheral. I'll see the little bit of the design and I'll be able to tell it's Starbucks. So my error rate, hopefully, I'm an average human, is 5%. I could be worse, but hopefully I'm in the average of 5%. I'm definitely not better. Deep learning has gotten us to a 3% error rate on computer vision, right? So this is why you hear that computer models are now beating humans on vision and speech, right? The speech recognition on your phones, whether it's Google Voice, Apple Siri, is pretty damn good. And pretty soon, I think those assistants are going to become much more interactive than they are today. Right now, it's question and answer. I think it'll become more conversational as time goes on. So let me, I kind of said this when we started, but I want to tell you what IBM does in this space, right? So we kind of have products ranging in the whole space of machine learning and deep learning. If you look at this stack, right, the way we think about the problem is one of the hardest challenges that very few people will tell you about in this space is data preparation and data cleansing, right? Just getting the data from the format it's in into a format that is machine learnable, let's call it that, right? So even though that's on the side, data transform and data prep, but doing that piece of work is really hard. I was talking to a client recently, and they have a mix of databases where their data is coming in. Their point of sale data is in an Oracle style database, traditional RDBMS. They have streaming data coming in, and they also want to use other data such as weather data or social media data to inform their AI model. The problem is the data schemas are all different, and even if you put all the data schemas into one in a Hadoop cluster, now the problem is the trained AI model schema is different from your production data formats. So you have to actually backport the AI model to your original schemas. There's a layer of distributed computing. A lot of our clients are using Spark as a way to manage a cluster. Some are using MPI. And of course, machine learning frameworks such as H2O. I should have added H2O there. Now, on top of that, you're seeing more and more pre-built APIs come into the market, right? Watson obviously is one of them, but we have competitors from Google, Azure, Amazon who are doing vision APIs, speech APIs. We have a sentiment analysis API. And so again, it comes down to who the target there is. So Watson sort of operates on the highest level there where they're doing mostly APIs. They do have the things below that as well available to data scientists. So all machine learning as a service is available on IBM Cloud. What I focus on is what's called PowerAI there, which is the set of machine learning and deep learning libraries and frameworks and the hardware infrastructure that goes with it. Oops. There we go. So what we've done is, one of the challenges in the market right now, at least at enterprise clients, is if you want to get TensorFlow Cafe, you got to go to the open source and get them. There is no enterprise offering. So what we did was we built an enterprise offering called PowerAI, which essentially takes TensorFlow Cafe, all of that stuff, curates it, tests it, validates it, and we add support. We bring support to it. Very much like H2O has an enterprise offering. So we have PowerAI, which is an enterprise offering of the deep learning frameworks. But then we enhance it. We add tools to make it easier to use the open source frameworks. We also add performance libraries to make these frameworks run faster. So I'm going to give you, because I have only 18 minutes today, so this is supposed to be a fire chat. I'm going to give you, sort of points here and there on each of those things next, right? What are we doing for developer tools? What are we doing for performance? So one of the tools we've built is a tool called PowerAI Vision. This is a tool that, given any image or video data set, automatically generates a trained deep learning model, and in fact generates either a REST API or a inference, it maps it to either an embedded GPU, a full GPU, or an FPGA. So it does end-to-end. All you need to give it is image data set and video data set. It picks the model, it picks the hyperparameters, it does the hyperparameter tuning, it does the data management, model management, all of that stuff. And in fact, it has a tool, a sub-feature, which enables you to do semi-automatic image labeling. So I'll describe it because I don't have the time to show you a demo, but take an image, or if you have let's say a video set, right, a video, you can freeze frames in it, draw a box, so you just pull down a box, put a label on it. You do that, let's say, for 25 frames. So you label manually 25 frames. You tell it train. It trains a model based on that limited amount of labels. Then you can use that trained AI model to label the rest of the video. And let's say at that point your accuracy is like 55, 60%, right? You now go in and fix another 25 frames. So you go into 25 more frames and fix the labels that it's done. So half of them will be wrong, half of them will be right. And you fix them. You say train, auto label again. So you're iteratively training the model to become good at labeling, right? And in fact, you're also training the model at the same time. What happens is, what we've seen in practice here is you usually start around 56, 57% accuracy on the first auto label. It goes up into the mid-60s in the second. So it keeps going up by 10% every time you run it, or fix some labels and rerun it. So that feature alone is actually extremely valuable to a lot of data scientists. But because this whole software actually does an entire AI model, is really designed to get a person who's a novice in machine learning and deep learning to be able to use deep learning to build a trained AI model for image and video data set. So you can try it out. It's available online for you to try. The other feature we've added on top of TensorFlow and Caffe and others is a auto hyperparameter tuner. What this does is, hyperparameters can be complex. You have to do multiple iterations over tens, if not hundreds of hyperparameters to try to find the best set while you're trying to train an AI model. We do it automatically for you. We have 3 different implementations. One is a random implementation, randomly picking hyperparameters. The other is a tree-based Parson estimator. And the third is a Bayesian optimization. In most cases, the Bayesian optimization is the best auto hyperparameter tuner. Now, the way it works is the software automatically launches 100 or 200 training jobs with different hyperparameters. It essentially uses Apache Spark underneath to manage the job scheduling. You don't know any of this, by the way, in the sense you're operating in a GUI in which you say auto-tune, right? That's it. And now that GUI is going to show you graphs of how the tuning is going, what hyperparameters are happening, how many training jobs are running. Under the hood, we're running Spark with, let's say, 100 different deep learning training jobs on as much infrastructure as you have in the back end. And it, in the end, comes out with the best hyperparameters that it can find. And it's pretty, in most cases, it beats humans, by the way. You have to be a real expert at hyperparameter tuning to beat this. And you have to spend much more time, weeks, if not months, to beat this tool, which can get you the job in a few days. So I'm going through a lot of features very quickly. So each slide is not related to the other, so I apologize for that because trying to work against the clock here. So I talked about the PowerAI vision tool. I talked about auto hyperparameter tuning. The third thing we've done is we've built a distributed deep learning library. So if you take TensorFlow and Caffe off the web, they scale extremely well with GPUs in a single server. So you go from 4 GPUs to 8 GPUs, you'll see pretty good scaling. It's almost linear scaling. The minute you add a second server, some of this software doesn't even support multiple servers. I think Caffe still natively does not support multiple servers. May have changed, I don't stay up to date, but TensorFlow I know does, but doesn't do a very good job of scaling to multiple servers. We've built a library that hooks into all of these frameworks, any frameworks. It has a standard API, and it uses MPI, which is a message passing interface. MPI is a message passing protocol from the HPC space. And we're able to get linear, almost linear scaling. So this is over 256 GPUs in 64 servers. We have 95% scaling. Now, there's a lot of advantages, by the way, of scaling. The number one advantage is the training time, right? In this case, a full training of ImageNet 20K with a ResNet 101 model would take 16 days on a single system with 4 GPUs and takes 7 hours on this 64 system scaled out version. Now, you can translate this into any training you do. If your training is taking 4 hours, if you use 4 of our systems, you'll get the training done in 1 hour. So in a sense, we do almost linear scaling with the number of servers you have. The other big advantage of this is often people, when they're trying to get, this can also improve accuracy in a weird way because people play with batch sizes to get the training time down, but that often is at the cost of reduced accuracy. So the work we did here, which is a published paper, is the best scaling achieved so far. No one has been able to beat it. The closest anyone got was a team from Facebook research from Jan LeCun. We beat them. They're at 89%. We're at 95%. And our accuracy is higher, too. So this is also the most accurate image classification in the world. And the previous record was held by Microsoft. They were at 29.4%. We're at 33.8, whatever, about 4% more. To put that in context, previous improvements have been 0.2%. So we improved by 4% in one leap. Most other works, they're happy when they're like, I beat the other guy by 0.2%, right? So there's a lot of advantage of scaling is the bottom line here, right? Of being able to take advantage of a large cluster to do your deep learning. Now, we've taken all of this software and put it into a workbench targeted at data scientists, right? What we've done is, so by the way, all of these are pieces available as pieces, but they're also available as a complete workbench. We have a product called Data Science Experience, which has Jupyter Notebooks, RStudio as the front end. It has model management, data management. It enables you to add any machine learning or deep learning libraries in it. So the PowerAI software, which is what I've been talking about so far, hooks into Data Science Experience. H2O hooks into Data Science Experience. Anaconda hooks into Data Science Experience. But the aim we have is to give data scientists the developer tools that they need in a complete way. And this is available both on-prem and in the cloud. A lot of the clients we work with, larger enterprises, the data is still on-prem, because often they have a mix of, let's say in the case of retail, point of sale data. In the case of banks, a lot of banking data that they want to keep on-prem. So all available in one tool or separately as well. So I want to shift gears on one aspect. So I've been talking a lot about software. I want to talk a little bit about hardware. This morning, we announced a new server for deep learning and AI. As far as I know, this is the fastest server in the world for deep learning and AI right now. And the reason is, I'll show you on the next slides. I'll prove it with benchmarks on the next slide. But the fundamental reason is what we've done is we have an IBM Power 9 CPU. So this is, it's not Intel. It's IBM Power. But it runs Linux. It's pretty standard. You can't tell. If you're using Linux, you can't tell what you're using underneath. But the advantage you get is we've embedded a high-speed interface called NVLink into our CPU that's also embedded in NVIDIA's Volta GPU. So we have a very high-speed private connection with NVIDIA's GPUs. We don't need to use PCIe. And our interface is 6 times faster than PCIe. So if you look at this chart, and I wish I could, I can almost not point there, but let me see if I can. But I'll say it. Like, what happens is the CPU has a big system memory. We can connect 0.5 terabyte to the CPU. And the connection is very fast. We are, in fact, faster than Intel. We can do 170 gigabytes per second. But what happens is in Intel-based systems, you have PCIe that's connecting the CPU to the GPU. So your model and data is sitting in the CPU, and it gets choked by the PCIe. Often, if people are, let's say, operating with very large images, if you have a real image, which is a medical image or a satellite image, it's a very high resolution. And the problem is, as image data sets grow, so does the model size. So, because the first layer, for example, has to be very large if your image is very large. And then the results generated by the first layer is much larger because of the first layer. So what most people do is they either downsample images, which means you lose accuracy, or they break up the image, which actually can really screw up your training because you're not learning on the ground truth anymore. You're learning on pieces of the image. We allow you to use the entire image, no matter how big it is, as long as it can fit in 0.5 terabyte of memory with a very large model. Because we have a very high-speed connection, which is 6 times faster than Intel's, we're able to transfer that image in small chunks to the GPU, compute it, and move it back. And so you can do this much faster and still achieve the speed up. So this system can do up to 6 GPUs and 2 of our CPUs. These are the results. What you'll see here is we've taken 2 different models, Chainer and Caffe, to demonstrate large model support. And this was using the image size was 2,560 by 2,560. So we took ImageNet and we just scaled up the images to make them pretty large because this was meant to be a test, right? So we took an enlarged Google Net model and an enlarged image net model just to demonstrate the point. We have real customers doing medical imaging using this, so we do have real clients. I just can't share real client data. And what you see is we get a 3.7 to 3.8x speed up over Intel-based systems when you have large data sets. Right? So, and this is all coming from the fact that we're able to communicate the data and the image, the data and the model between the CPU and GPU much faster. So I talked about how we built the PowerAI software and enhanced TensorFlow and Caffe, right? So we have tricks, which are software tricks, or tricks is the wrong word, but we have methods, which are software methods like distributed deep learning. We also have hardware methods, which are connections between the CPU and GPU that enable us to do things on performance. And then we have ease of use tools. So that was my last slide. You can learn more on our developer website, which is, the URL is right there. And I'm happy to take questions now. I think we're using Slido to do the questions. Someone please ask a question so I feel good. I'm just kidding. So while we wait, yeah, go for it. Yeah. So the question is, on one of the slides, we talked about a cluster, the distributed deep learning running on 256 GPUs. Was that a single cluster? Yeah, absolutely. So what we did was that was 64 servers tied together in a single cluster and with a very high-speed network. So the network we used in that case was Mellanox's InfiniBand. So that's how we got the 95% scaling. You do need, obviously, when you go to multiple servers, a tightly clustered system. If you use an Ethernet-based system, you'll get about 60 to 65% scaling. And if you use stock TensorFlow from the web, I think you get around 30%, although someone from the TensorFlow team might object if they're here. So the question is, have you tested the distributed deep learning against most of the popular frameworks like TensorFlow, et cetera? Absolutely. So we have results for TensorFlow, Torch, Chainer, and Caffe. Those are the 4 we've tested. And they're all about the same, by the way, 95%-ish scaling in all of them. The large memory support, as I showed you right now, we showed on Caffe and Chainer, that we're currently working on TensorFlow. There is let's call it an issue in TensorFlow that's preventing us to use large model support there right now. Okay. I can't read it there, so I have to read it here. Okay, so do you see deep learning models replacing traditional machine learning models? So I think it goes back to that first slide I showed you where it totally depends on the amount of data you have, right? The more data you have, the more accurate deep learning becomes. Right? So I don't see this as competition as much as you look at what you have and you figure out what the right model is. Just the same way you used to choose between all of these different things. There was a very, everyone should go look this up. I dropped the slide in the interest of time. But Kaggle just did a survey of all the popular machine and deep learning methods. The number one method by a mile was logical regression. Right? So despite all that hype and the Google trends and all that stuff, deep learning was like 3% or something like that in the whole damn thing, right? So I get it. There's value here. There's huge value. We all believe there's value. But adoption is going to take time. The biggest challenge for deep learning right now is most people who use images and speech and have straightforward data, I call it, it's easy to use these methods. There's a lot of pre-existing work to use them. When you have text data, which is common in enterprises, there's a lot of data preparation and data cleansing that you have to do. And you have to have enough data. How do you do semi-automatic labeling for data? We haven't figured that out yet. So, in fact, that's an active research project. Images are easy in many ways because, it's for a human to look at an image and draw a box and create a label is easy. doing that with text data is hard to do. And so that's an active research project for us, definitely the next thing we want to go do. And by the way, in that, we're looking for collaborators. So if anybody wants to partner with us, we're happy to partner. Any questions from the audience? Is that we good? All right, thank you very much.